Welcome to TJC Physics. I am going to do today an example of a Physics 1118 problem. I believe this problem comes out of the OpenStax College Physics textbook, and it's a one-dimensional kinematics example. So this question basically states that we have a train traveling on a straight, level track, so a one-dimensional problem. It has an initial speed of 35 kilometers an hour, and it's going to travel 200 meters while accelerating, speeding up at 1.50 meters per second squared. We're going to determine A, what is the speed of the train at the end of this distance, and how much time did it take for the train to travel that 200 meters. There are generally a few steps that you can use in any type of problem solving, no matter what the type of physics problem. Step 1, draw a picture of the problem and include a coordinate system. This helps you visualize the problem and figure out what exactly you're trying to solve. You don't have to make it an artistic masterpiece. As you'll see, my artistic skills leave a lot to be desired, but it should be clear and indicate a good coordinate system on it. I'll assume the train is traveling to the right at a starting initial velocity v0 of 35 kilometers an hour to the right. I'll put on my coordinate system, the positive x-axis pointing to the right. Using this coordinate system, I'll set the initial position x0 to be at 0 meters, and I'll set the final position, which we're looking at the end of the problem, to be at 200 meters to the right. So x final, xf, will be 200 meters. At that final position, it'll be moving at some unknown vf, its final velocity, but it will be accelerating to the right at 1.50 meters per second squared. Because the problem states the train is speeding up, the velocity vector and the acceleration vector have to be pointing in the same direction. Step 2 is write what you know and don't know. Summarize the variables you're going to be using. So for this problem, for instance, what we'll be interested in is initial position, final position, initial velocity, final velocity, the acceleration of the train, and the time. So we know the initial position will be at 0 meters and the final position will be at 200 meters. Now, you've probably noticed the initial velocity was given in terms of kilometers per hour. That doesn't match up with our units for acceleration or position. We want to convert that kilometers an hour to meters per second. Now you can try that calculation on your own, but you will come up with the answer 9.72 meters per second. Now the final velocity we don't know, but we also know the acceleration is plus 1.50 meters per second squared, and the time of travel is unknown as well. So at this point we've been able to list everything we know and don't know. I like step 1 and step 2 because even though we haven't done any mathematics or solved the problem yet, we've got a handle on the problem now. You've visualized it, and we're ready for step 3. And that is list equations of use to me. Or of use to use, I should be. So in this case, for this type of one-dimensional kinematics problem, I'm going to list 3 of the most popular kinematics equations to use. You will have seen these in class. So now that we've got these 3 equations, we can pick the best one to solve for our unknowns. In this case, looking for VF. I want to notice that I have V0 already, I have acceleration, and I have my displacement. So equation 3 looks like it'll probably be the best or easiest equation to use. So with this equation, I will move on to step 4. So step 4 is to solve the equations for the unknown. So we'll start with our equation. It won't require any manipulation because we are just going to try and solve for VF. So now the next step is to put the numbers in. And just notice that delta x is x final, take away x initial, which is why it's 200 minus 0. And if we do that, we come up with an answer for VF squared, plugging into our calculator, of 694.478 meters squared divided by second squared. Now, if there's one thing high school algebra has taught us, it's that when you take the square root of a number, you end up getting 2 solutions, a positive and a negative. But in physics, only one of those solutions will have a meaningful connection to the problem. So we get VF is equal to plus 26.4 meters per second or negative 26.4 meters per second. Now, we want to take the one that's more meaningful to us in this situation. And since we're moving in the positive direction along the positive x-axis, I think you can probably see that the answer will be plus 26.4 meters per second. So we can ignore the negative 26.4 meters per second because that would indicate that the train was moving to the left, which it's not going to do. It's not consistent with the problem. Thus, our final answer for part A is 26.4 meters per second. Now we still have to do part B, so I'll scroll down a little bit, and we're going to need one of the equations. Now I think equation number 2 is going to work the best because we know the final velocity, the initial velocity, and the acceleration. So we can actually manipulate that equation to solve for time. Time will equal final velocity, take away initial velocity, divided by acceleration. And now I'll just plug in some numbers. Final velocity is plus 26.4 meters per second. Initial velocity was 9.72 meters per second, and acceleration was 1.50 meters per second squared. You will come up with a time of 11.1 seconds. All right, so we have our answers for part A and part B. Step 5 is, does your answer make sense? Here's where you reflect on your answers to see if they make sense in terms of the problem. This isn't always easy, and it comes with experience. Now, if you look at those two numbers, 26.4 meters per second and 11.1 seconds, those seem like realistic, accessible numbers that match the problem. They don't seem unreasonable at all. I've seen students solve this problem and forget to take the square root and just write down that the train was going at 694.478 meters per second. That is like twice the speed of sound. The train is not doing that in this case. And that should be something that sort of clicks into your brain and goes, maybe I need to go back and relook at the algebra. I probably just made a simple little mistake. And I think in this case, the answer is definitely yes. Also notice that I included units with my answer. This is very important because physics deals with quantities. Well, that brings us to the end of this video. Hopefully it will help you on your problem-solving journey. And I'm adding new videos all the time, so if you want to subscribe to the channel, you can just click on the button I'm about to show. And thanks for watching, and have a great day.